Hello students, welcome to EPG Pathshala Biophysics. I am Dr. Ravi Majumdar, Emeritus Professor, Department of Natural Sciences, West Bengal University of Technology, Kolkata, and formerly I was Professor and Head, Biophysics Division, Shaha Institute of Nuclear Physics in Kolkata. Today we will talk about energy levels, atomic orbitals, and electron probability densities in hydrogen atom. Name of the paper, as you all know, is Quantum Biophysics. What are we going to learn from today's lecture? These are solutions for energy levels and wave functions of hydrogen atom. Energy levels are identical to those in Bohr model. Atomic orbitals are tabulated for K and L shells. And probability distributions for S and P electrons are shown. The energy levels and wave functions for a hydrogen atom is determined by solving Schrodinger equation in 3 dimensions. Since the electron in hydrogen atom is under the influence of an attractive Coulomb potential, which is spherically symmetric, the Schrodinger equation is solved in spherical coordinates. The energy levels are obtained by solving the radial part of the Schrodinger equation only. The result agrees completely with those of the Bohr model. Solution of the angular part, on the other hand, is similar to that of a rigid rotator, about which we have learned in the previous lecture. The wave functions, or the atomic orbitals as they are called, are tabulated for K and M shells, which assume simpler forms. It may be noted that in most commonly occurring atoms, like hydrogen, nitrogen, oxygen, and carbon, in biologically important molecules, the electrons are restricted to K and L shells in their ground states. Nature of the 1s, 2s, and 2p orbitals, as well as the electron probability distributions, are described in detail. Let us now tell you about the objectives of this lecture. Schrodinger equation is solved in spherical coordinates for Coulomb potential to obtain the energy levels and wave functions of the hydrogen atom. Energy levels are identical to those obtained from the Bohr model. Wave functions, or the atomic orbitals, are tabulated for K and L shells. Nature of the 1s, 2s, and 2p orbitals, as well as the electron probability distributions, are described in detail. First of all, let me talk about the Coulomb potential, which can be described as a Coulomb well. Now, the electron in an atom is bound to the nucleus by a spherically symmetric Coulomb potential, Vr equal to minus k Z squared by R. By spherically symmetric potential, I mean a potential which is constant over the surface of a sphere. It's a function only of R, and it doesn't depend on theta and phi. So in this equation, if you put Z equal to 1, this will describe the potential for a hydrogen atom, and K, which is the Coulomb constant, that's equal to 8.99 into 10 to the power 9 units. So this is a 3-dimensional Coulomb well obtained by plotting Vr against R, whose vertical cross-section looks like a curved cone. So you can see the figure. There's a Coulomb well with energy levels for hydrogen atom. So actually, you see, if you plot Vr against R, you will get a sort of 3-dimensional conical structure, and this is just the cross-section, the vertical cross-section of that cone. And the energy levels, these are the energy levels which are obtained from the Bohr model. And as I told you in the beginning, that you see by solving Schrodinger equation, we are going to get the same energy levels as we got in the case of Bohr model. So the energy levels are shown here in this figure. Now let's write down the Schrodinger equation for the hydrogen atom. So that's the usual Schrodinger equation, del square psi plus 2m by h cross square, E minus v psi equals 0. Now, where del square has to be written in spherical coordinates. If you express del square in spherical coordinates, then you get the second equation, which you can see on the screen. Okay, so this is a clumsy equation, but you see there's no escape because you have to face the situation. Now, you can separate the radial part of the wave function from its angular part. That is, the total wave function, which is a function of r theta phi, that can always be written as a product of a radial wave function r and the angular wave function theta and phi. In the case of rigid rotator, you see r was constant, so we only had y of theta and phi. But here, you see all r theta and phi vary because this is a real three-dimensional problem, and you see the radial part comes as a component of the total wave function. So in view of the probabilistic interpretation of the wave function, a separation like this is plausible. Well, let me explain this a little bit because I have used this several times. Because r, that's the radial wave function. So if you square it up, r square, you see, that tells you about the probability of observing a particle on the surface of a sphere, okay, for a given r, that is on the surface of a sphere. And if you want to find out the probability of observing the particle at a particular point on the sphere, then you have to multiply it by y square. You see, that will r square times y square will give you the sort of probability, that is psi square actually, will give you the probability of observing the electron at a given point on the sphere, okay? Because you see, it's a question of compound probability, that it's the product of two probabilities that will give you the probability of observing the electron at a distance r from the nucleus and also at a given point where on the sphere which is characterized by the two angles theta and phi. Now, putting this in Schrodinger equation and rearranging terms, well, as we did before, you see, this is similar to what we did in the case of rigid rotator. So we put this separation into the Schrodinger equation and then, you see, rearrange the terms so that, you see, the left-hand side becomes a function of r only and the right-hand side is a function of theta and phi only, because see, this is y theta phi, so, and this is rr. So right-hand side is a function of theta and phi. So as before, we have to sort of equate each side to beta. That's what we have said. The left-hand side of this equation is a function of the variable r only, and the right side is a function of the angular variables theta phi only. So each side is equated to a constant or a separation parameter beta. As a result, the Schrodinger equation separates into a radial equation and an angular equation. So the first one is the radial equation and the second one is the angular equation. We don't have to bother very much about the angular equation because you see, this is the same equation as we got in the case of a rigid rotator. So we know the solutions, so we'll just sort of summarize them, those solutions at the end. And the new thing is the radial part of the equation, Schrodinger equation, and this is very important because it contains the potential VR, that is the spherically symmetric potential, which is a function of r only, appears only in the radial part of the equation. And since the energy is also there in this equation, so if we solve this equation, we will get the discrete values of the energy as well as the radial part of the wave function. So after getting the radial part of the wave function, you see, we'll multiply it by the angular part of the wave function to get the total wave function for an electron in hydrogen atom. So the last equation is identical to that for a rigid rotator, though the parameter, this is important, though the parameter beta does not contain energy E in this case. The energy E and the potential VR are present in the radial equation only. The angular equation does not contain the potential and can be solved exactly as in the case of a rigid rotator. For an electron inside the atom,
The angular momentum quantum number is denoted by L instead of J. The quantum number J is reserved for the total angular momentum of the electron, including spin. Thus, the solution of the angular part of the equation restricts the value of beta to L into L plus 1, as in the case of a rigid rotator. So putting beta equal to L into L plus 1 and VR equal to minus kZd squared by R, that is the Coulomb potential, the radial equation becomes like this. That is the first equation which you can see on the screen. Or you can rewrite this in the form d dr r squared dr plus 2I by h cross square E minus V times R equal to 0, where I equal to mr squared is the moment of inertia of the electron about an axis passing through the nucleus, and VE is the effective potential, which is equal to the Coulomb potential plus the term L into L plus 1 h cross square upon 2I. Well, that's VE. And I is the moment of inertia of the electron about an axis passing through the nucleus. Here, it is important to recognize that the second term of this equation, that is the equation for VER, the effective potential, is the rotational kinetic energy of the electron, which effectively reduces the attractive potential energy, except when L equal to 0. This is known as the centrifugal barrier effect, which is absent only for an S electron where L equal to 0. Okay? You see, what we have shown is that the effective potential is the Coulomb potential and plus, you see, a potential which is called the centrifugal barrier effect. And this is pictorially represented in the figure. So when L equal to 0, this is pure Coulomb potential. But when you have L equal to 1, L equal to 2, and L equal to 3, you see the centrifugal barrier effect sort of changes this curve in the manner which you can see in the figure. So instead of going down, you see for L, as in L equal to 0, it reaches a minimum and then goes up, okay? Because the centrifugal barrier is sort of, it opposes the Coulomb potential, okay? And therefore, you get, this is the plot of the effective potential against R. This is the effect of centrifugal barrier on Coulomb potential. Now the solution of radial part, the energy levels. So we can rewrite the radial part of the equation like this. So now here what we are doing is just sort of some manipulations, mathematical manipulations. So introduce a new variable UR equal to RR. And so this is the second equation is the radial equation in terms of U, or the third equation is also the same. You see where you have introduced R0 square, well, is equal to h cross square upon 2 me and a constant b which is equal to k mz square by h cross square. This is just for convenience. Now note that R0 has the dimension of length. So if we introduce in yet another new variable rho, which is equal to 2r by r0, then rho is a dimensionless quantity. Then you see you have this equation. Now since rho lies between 0 and infinity, the asymptotic form of this equation is d square u d rho square minus 1/4 u equal to 0. Asymptotic solutions are e to the power plus minus rho by 2. The acceptable solution, which remains finite for rho tending to infinity, is the one with negative sign in the exponential. So the general solution can be expressed as u rho equal to e to the power minus rho by 2, taking the negative sign, and then multiplied by v rho. Now if you plug this in the main radial equation, then you find that this new function v rho satisfies this equation d square v d rho square minus dv d rho plus within bracket br0 by rho minus l into l plus 1 by rho square times b equal to 0. Now it is tricky to solve this equation as it has singularity as rho equal to 0. Without going into details, it is sufficient to know that the solution can be expressed in the form v rho equal to rho to the power l plus 1 into l rho, where l rho is a new function. This satisfies the equation which appears as the first equation on the screen right now. So it may be recognized that this leads to an associated Laguerre equation provided we set BR0 equal to n, where n is equal to 1, 2, 3, and so on, and introduce the numbers p equal to 2l plus 1 and m equal to n plus n. The equation then becomes, you see, rho d square l d rho square plus p plus 1 minus rho times dl d rho plus m minus p times l equal to 0. So this is clearly an associated logarithm equation where L rho are the associated logarithm polynomial, which is L rho equal to L mp rho, and then L, which is equal to n plus L and 2l plus 1 rho, where L equal to 0, 1, 2, and so on up to n minus 1. Now the condition BR0 equal to n, you see, gives the energy level, because B contains the energy. When we defined B, we found that it contains the energy. So the discrete energy levels are immediately can be written down. You see, once you identify this relation, that BR0 has to be equal to n. Okay, so this gives the discrete set of energy levels, and this result agrees completely with the Bohr model. The new information is that corresponding radial wave functions can be obtained, you see, from u rho equal to e to the power minus rho by 2 v rho, and which turns out to be e to the power minus rho by 2 rho to the power l plus 1 and the logarithm function. Now, recalling r equal to ur by r and rho equal to 2r by r0, the radial wave functions with appropriate quantum numbers are written on the screen. That is the second equation on the screen, where n are the normalization constants. Well, n depends on small n and small l. So these are normalization constants. So these constants are determined by using the normalization condition for the radial function as follows. That is, the radial wave function should be normalized to unity. And you see, here you can find an integral, okay, which can be evaluated by from the known properties of the logarithm functions. So this is a known integral involving the logarithm functions. So this result is given here. This is the very important result, because you had obtained the energy levels. Now you obtain the complete radial wave function, normalized radial wave functions, the expression for r, nl, r, which you can see on the board, where you see rho is 2z by n, r by a, and a is the Bohr radius, h cross square by k me square. Okay, so you can express the radial wave function in terms of rho and a. So now comes the solution of the angular part. The angular wave function can be further separated as y as a product of theta and phi, leading to the two equations, the one theta equation and the phi equation. Now these do not involve the potential, and the solutions are the same as in the case of a rigid rotator, leading to the normalized wave functions, which you can see on the board. That's the expression, that's the normalized wave function, capital theta Lm as a function of small theta. So that's the angular part of that's the theta wave function, and then you write the phi wave function. So where m is equal to minus L, 0, and so on, up to plus L. So what we have learned by solving Schrodinger equation for hydrogen atom, so on the screen you can see the complete solution. That's a summary of complete solution for energy and wave functions. Once again, I tell you that the energy levels are given by the same expression as you obtained from the Bohr model, and the total wave function is the product of the radial part and the angular parts of the wave function. You have found out the radial part of the wave function, r, nl, r, in terms of the logarithm polynomial logarithm function, and you have obtained the ylm, that is the angular part of the wave function, a spherical harmonic, in terms of the associated Legendre function or Legendre polynomial. And what about the quantum numbers? You see, n is equal to 1, 2, 3, and so on. And so these are referred to k, l, and m shells. And then the quantum number L can take values from 0, 1, 2, and so on. Its minimum value is 0, but maximum value is not n, but n minus 1. Okay, and so these refer to s, p, d, and so on orbitals, and m, that is called the magnetic quantum number. So this has 2l plus 1 values, okay, as shown, and these refer to the orientations in space. Okay, now you see we show the table for wave functions, and these are the complete atomic orbitals. You see the wave functions are usually called atomic orbitals. You see, because you see in quantum mechanics we don't have orbits. We have only wave functions which describe the electron charge distributions. You see, so that is why you see the wave functions, these are called orbitals, as if they are replacing the idea of orbits in classical mechanics. That's why these are called orbitals. So these are the wave functions or complete atomic orbitals for k and L shells, where rho is 2z by n times r divided by a, where a is the Bohr radius. These wave functions are usually complicated, but they assume simple forms for lower values of n, l, m, such as k and L shells. Okay, so you see, when I write down the wave functions for k, l, and L shells, then these are not that frightening. These because you see those spherical harmonics and other you see polynomials, you see they take simpler forms, you see, for lower values of the quantum number n. So for k shell corresponds to n equal to 1, and L shell corresponds to n equal to 2. So you see the thing which you get here for psi n l m r theta phi, well, these are not so complicated. So all that you can see is that when you are considering the 1s and 2s orbitals, well, here you have the wave function does not have any angular dependence. It depends only on rho, and rho contains the radius. So the wave function depends only on the radius in the case of s orbitals, and therefore these are constant on the surface of a sphere, or these are spherically symmetric wave functions. But the same is not the case for p orbitals. Well, you can see that the p orbitals depend on angles theta and phi as well. Okay, now why do we sort of tabulate the orbitals for k and L shells only? That's because, you see, the basic components of living molecules in living cell, well, these are hydrogen, carbon, nitrogen, and oxygen atoms. And all these atoms have electrons in k and L shells in the ground state. Okay, let me just explain to you a little bit more, that when you are considering k shell, n is equal to 1, so L can be equal to 0 only, and m also is 0. So this orbital is 1s orbital, and you write down the corresponding wave function or the atom, and then you see for the L shell you have n4 possibilities, because n is equal to 2, so L can be 0 or 1. And if L is equal to 0, m is also equal to 0. But if L is 1, m can be 0, 1, and minus 1. So that gives 4 possibility. So the energy level, you see, that is 4-fold degenerate. Well, there are 4 states corresponding, or 4 atomic orbitals belonging to the same energy level E2, and those atomic orbitals are listed in this table. So the first of this, as I said, is spherically symmetric, and the remaining 3, you see, they have angular dependence. So let us see how these will look like, pictorially.
Based on the table which you have seen on the screen, we shall now see that an atom is no longer viewed as electrons orbiting the nucleus in a series of circular and elliptical orbits. In quantum mechanics, the picture of orbiting electrons reduces to a picture of probability distributions. As a result, the electrons are smeared out into charge clouds that do not change with time. Well, it's a stationary picture for the atom which does not change with time. In hydrogen atom, for example, we shall see that the 1s electron forms a smeared out charge cloud with a sphere of maximum density at a distance of Bohr radius from the nucleus.
So we will basically consider the shapes and behavior, of the atomic orbitals. Let us talk about the radial part of the wave function. Well, as I said, the table for wave functions shows that for 1s orbital, the wave function has no angular dependence. So the probability of observing the 1s electron at a distance r from the nucleus, which means that the probability of observing the electron between two spheres of radii r and r plus dr for hydrogen atom is, that is psi 100 square and multiply by 4 pi r square dr. That is the volume included between the two concentric spheres of radii r and r plus dr. So that's the probability of observing the electron at a distance r from the nucleus. That is 4 pi r square multiplied by the square of the radial wave function. Okay, so this can be written down as 4 by a cube r square e to the power minus 2r by a dr, because you can write down the value of psi 100 from the table which we have just discussed. So this is the probability of observing the electron at distance r from the nucleus. Let us now consider an example. Find the most probable distance of the electron from nucleus in the ground state of a hydrogen atom. So how do you do that? Well, in order to find the most probable distance, you have to differentiate this probability function with respect to r, okay, and put it to 0. So the probability function is, you leave out this constant, and the probability function is basically r square into e to the power minus 2r by a. So you differentiate that with respect to r and put it equal to 0. And if you do this exercise, you will get r equal to a, which means that the radial probability of the 1s electron is peaked at the Bohr radius. Okay. So that is why you get you can see the Bohr radius. You can identify the Bohr radius as the radius of the hydrogen atom. In the language of modern quantum mechanics, this is the distance from the nucleus where the electron is most likely to be. This is the maximum probability, right? So now you can see the picture on the screen. There's what is Bohr radius in modern quantum theory. Okay, so you have plotted the probability function against r, that is the radial probability function, and it is peaked at the Bohr radius r equal to a. And if you want to show this, okay, as a three-dimensional spherical distribution of electron cloud, okay, then E psi 100 square. Well, if you multiply the probability function by the charge, you get the charge density, or the density of the smeared out electron charge in quantum mechanics. So that's what you can see on the right side of the figure. And this figure is not very properly shown, but all that I wanted to stress is that there's a maximum probability of observing the electron at a distance r a from the proton, which is the Bohr radius. And the ring which you can see here, this gives actually the Bohr radius, or the radius of the hydrogen atom. Okay, now we come back to the angular part about which we were talking about. The table for wave function shows that the 1s and the 2s orbitals have no angular dependence, so that they represent spherical probability distributions. Okay, as we saw in the previous picture also, we saw a spherical, probability distribution, or a spherical charge distribution, that is replacing circular orbits of the Bohr model. So it looks as if the s electrons are smeared out into spherical charge clouds. Okay, that's exactly what we showed in the last figure. Here in this figure also we are showing the same. Okay, only we are not marking the Bohr radius here as the distance of maximum probability. So this shows the spherical probability distribution for 1s electron, or this is the same as for 2s electron also. Well, there you see the radius will be larger. You see for 1s electron, the charge density is peaked at the Bohr radius, well, as shown in the last figure. Well, and then we talk about the extended probability distributions or charge clouds for 2p electrons along x, y, and z axis. Table for wave functions also shows that the three 2p orbitals, which is L equal to 1, depend on the angles theta and phi. In 3 dimensions, these represent dumbbell-like extended probability distributions, replacing elliptical orbits of the Sommerfeld model. So comparing the angular dependence of 2p orbitals with those of the coordinates x, y, and z, it is found that these probability distributions or smeared out extended charge clouds for the p electrons are directed along the x, y, and z axis. So if you look into those that table, you see which gives the angular dependence of the wave functions, then you'll find that you see 2px, 2py, and 2pz orbitals. You see they are directed. They are sort of directed towards x, y, and z axis, and a closer look into the angular dependence also tells you that these are dumbbell-shaped distributions. Okay, s electrons had spherical charge distributions which had no direction, but for p electrons, well, you have three possibilities: 2px, 2py, 2pz. In each case, the charge distribution looks like a dumbbell, and you see these are directed along x, y, and z directions respectively.
Let us now summarize what we have learned from this lecture. The Schrodinger equation is solved for spherically symmetric Coulomb potential to obtain the energy levels and the atomic orbitals for hydrogen. Energy levels are identical to those obtained from the Bohr model, and the atomic orbitals, which assume simpler forms for K and L shells, are tabulated. Shapes of the 1s, 2s, and 2p orbitals, as well as the electron probability distributions, are described in detail. Thank you.